Why are CFD simulations so slow? Mechanical engineering. Imagine trying to solve a giant puzzle where each piece influences its neighbors, and you need to do this millions of times. That's what CFD simulations are like. They involve solving complex math equations that describe how fluids move, heat transfer, and other physical phenomena. These equations are called the Navier-Stokes equations, and they are nonlinear and coupled, meaning they depend on each other in complicated ways. To get accurate results, CFD software divides the entire fluid domain into tiny pieces called cells or grid points. Sometimes, these grids have over 100 trillion points in high-fidelity simulations. That's a huge number, and each one needs calculations. The process requires a lot of computational power because it's not just about solving the equations once. It's about solving them repeatedly over many small time steps, especially if the problem involves changing conditions over time. Each step involves solving large systems of equations, which can take a lot of time, especially when the flow is turbulent or involves multiple phases like liquids and gases. Turbulence models add even more calculations because they try to approximate chaotic flow patterns that are impossible to resolve directly. Another reason CFD simulations are slow is the size of the mesh or grid used. To accurately capture details in complex shapes like engines, turbines, or heat exchangers, engineers need very fine meshes. The finer the mesh, the more cells there are, and the longer the calculations take. For example, a detailed simulation of an aircraft wing might use hundreds of millions of cells, pushing the limits of current supercomputers. Time stepping is also a factor. Small time steps are necessary to keep the simulation stable and accurate. But smaller steps mean more iterations, which extend the total simulation time. Plus, many simulations requiring multiple iterations to reach a point where the results stabilize or converge. This iterative process can take hours, days, or even weeks, depending on the problem size and hardware. Data movement is another bottleneck. CFD calculations involve moving huge amounts of data between processors and memory. Even with powerful supercomputers, this data exchange can slow things down because it takes time to transfer information back and forth. When dealing with billions of fluid parcels, this communication overhead becomes a major limiting factor. Physical model complexity also plays a role. More detailed models, like those including turbulence, chemical reactions, or multiphase flows, add layers of calculations. Simplified models run faster but may not give the detailed insights engineers need. Detailed models requiring more computing resources and time. Software and algorithms are also factors. Traditional CFD solvers use methods like the finite volume method, which balances accuracy and speed but still faces challenges with large, complex problems. Recent advances, like GPU acceleration and artificial intelligence-assisted simulations, are helping speed things up. However, the fundamental physics and the scale of the problems keep CFD simulations computationally demanding. In the end, CFD simulations are slow because they involve solving huge, complex mathematical problems with high accuracy. They requiring processing vast amounts of data and performing many iterative calculations. While hardware improvements and smarter algorithms are making progress, the physics and size of these problems mean that CFD will always need significant computational resources. That's why engineers often balance the level of detail with available computing power to get results in a reasonable time.